Okay, so let's do a sample problem. So here we have an example 16.8. So ammonia gas is dissolved in a 1 times 10 minus 4 molar solution of copper sulfate. I'll remind you that's copper 2 plus because the sulfate is SO42 minus, to give an equilibrium concentration for ammonia of 1.6 times 10 minus 3 molar. Calculate the concentration of copper 2 ions in solution. Okay, so this at first seems pretty difficult. And the setup is a little challenging, but once we get through the setup, it's very straightforward. Okay, and so if we think about our expectations, okay, we expect that the concentration of copper 2 plus at equilibrium will be very small. And the reason for that, if I back up, right, this is the same example we're talking about here. We know the Kf for the tetramine copper 2 ion is large. Consequently, its Kd is small. So we're going to expect that our free copper concentration is going to be small. You should always work out these expectations when we have these complicated problems. And now we can attempt to solve this problem either using Kf or Kd. Either way will work because it's the same reaction. I'm going to do this with Kd. Okay, so I'm going to write here that we know for one that we're talking about copper sulfate and we're adding ammonia to it. So let's just first write that first reaction just so we can kind of get a sense for what's going on. So that's aqueous, and this is reacting with dissolved gaseous ammonia. And that's going to be basically a full-on forward reaction making my complex ion, okay? So now that means I need 4 of these, and this will be aqueous. And what that also means is the sulfate remains in solution, okay? So if I'm starting off with 1.0 times 10 to the minus 4 molar of the copper sulfate initially, and all of this ammonia gas is dissolved into that, because the formation of this complex ion is really, really large, we're going to assume that all of this makes, so that entire 1 times 10 minus 4 molar copper sulfate becomes 1 times 10 minus 4 tetramine copper 2, the complex ion. Okay, and we can make that assumption because once again, we know the Kf of this is very large. So we're going to assume in this first step that that all becomes this. So now I'm going to set this up as a rice table, and I'm going to set it up with the opposite reaction, and hopefully you'll see why that is in a moment. So let's go through our rice table. So now we're going to say this is in equilibrium with free copper and 4 NH3s. Okay, beautiful. And then now when we go to start putting things in here, what we're going to assume in our initial state is that we have 1 times 10 to the minus 4 molar of this stuff, just from having the ammonia and copper 2 present. We're going to assume it all becomes that. Okay. So we're also going to assume now that we have 0 copper because we need to figure out what its equilibrium concentration is. And then they also told us here that we already know that our equilibrium concentration of ammonia is 1.6 times 10 minus 3 molar. So we already know that, which is cool. So we'll just put this term right down there directly. 1.60 times 10 minus 3 molar. So they already told us that. Okay. And so now what that means was if we were assuming that this was 0 to begin with, we know that that's got to increase by 4x. We know that has to increase by x, and that has to decrease by x. So when I go and put this all together now, because I know here now that my Kd is very, very small, we're going to be able to assume the value of x is also small, not only compared to the 1.6 times 10 minus 3, but compared to the 1.0 times 10 minus 4. So that means this becomes 1.0 times 10 minus 4. This is x, and this is 1.6 times 10 minus 3. So you can see here now, this setup is going to be pretty straightforward. So I'll remind you, my KD value we calculated to one significant digit was 2 times 10 to the minus 14. And now that's going to equal my ammonia concentration, which I already know what it is, times my copper concentration divided by this concentration. Okay, so I can now simply say that's going to be x times 1.0 times 1.60, sorry, times 10 to the minus 3, all divided by 1.0 times 10 to the minus 4. And now here, if I solve for x, so I can do that by multiplying this by 1 times 10 minus 4, and then dividing by 1.6 times 10 minus 3. And let's see here. I think I need to take that. Yes, I need to take that to the fourth power, right, because of the ammonias. So now we'll write all of that out so that's less confusing. So that's going to be 2 times 10 to the minus 14 times 1.0 times 10 to the minus 4, all divided by 1.60 times 10 to the minus 3 raised to the fourth power. Okay, so let's do that. So let's say that's 2e to the 14 negative equals, all right, times 1e to the 4 negative equals. And then now that's going to be divided by 1.6 times 10 to the minus 3 raised to the fourth power equals, and that is my copper concentration. That is the right answer. So that means here, so let's say we only had one significant digit, so 3 times 10 to the minus 7 molar. So I'll write up here, my copper 2 plus is 3 times 10 minus 7 molar. And we expected it to be really tiny, and in fact it is, and that makes good sense. Okay, and we'll do a lot more examples of problems like this in our live lecture meeting.